Welcome back to Maths with Mrs. J. Today I'm going to start talking about differentiation, and I want to derive the formula for how to differentiate from first principles. It sounds very tricky. It is a little bit tricky, but it's actually really interesting, and it's kind of cool to know what you're doing when you're differentiating and how you relate that to straight lines. So far, up to about year 10 level, you would have learnt about gradient of straight lines. And we said that the gradient is another word for slope or steepness. If we have a line that goes up from left to right across the page, then we say that the gradient is positive. And in this case, because it's a straight line, it's also constant. Every straight line will have a constant gradient. This one is going down from left to right across the page, so obviously the gradient will be negative. With a horizontal line, the gradient is 0. And with a vertical line, the gradient is undefined. Why? Well, we learnt a rule about gradient, and we said that gradient is rise over run, or you can think of it as change in your y value over change in your x value. With a vertical line, your run, or your change in x, is 0. And we should know by now that we can't divide by 0. That is not defined. Now that's all very well and all very exciting, but what happens about lines that are not straight lines? Say we had something like this. Say this was the side view of some sort of bike track that you were riding your bike along. You would very quickly find that the gradient or the steepness is changing as you go along this line. It's quite steeply uphill here. Then for a moment you're neither uphill nor downhill. Then you can probably stop pedaling for a bit, have a bit of a rest. Down the bottom of the hill again, you're neither going up nor down. Then you've got to go uphill again, etc. Here your legs would be really, really sore, I imagine. Now, we want to find some way of describing the gradient of a function at a particular point. And it makes sense that we talk about it at a particular x value. So if this is y equals f of x, for example, I haven't drawn my axes in, but let's just say that they're there somewhere, then the derivative function would be f dash x, which is kind of like saying what's the gradient at any particular value x. Now, we know already that to find the gradient we need 2 points. So we need to define what we mean by the gradient at a particular point. What do we mean by the gradient here? What we mean is, what we take it to mean is the gradient of the tangent to the curve at that point. That's meant to be a straight line. Then, of course, you can do your change in y on change in x. Now, normally, if you're differentiating, you are not going to do it from first principles. You will learn rules. There are heaps of rules that you can learn, and they're quite easy to learn and quite easy to work with. However, I would really like to change screens and take you through the process of how we actually derive this formula. Let's take a fairly simple curve. This is the curve y equals f of x. It looks a bit like a quadratic, doesn't it? It looks a bit like a parabola. And let's say this x value down here is x. And let's say the distance between these two x values here is h, where h is quite a small number. So this x value here will be x plus h, obviously. You'll see in a minute why I'm doing this. All right, the y value here, well, the formula for the line is y equals f of x. So the y value here will be f of that x value. The y value here will be f of x plus h, using the formula. Now we know that the gradient of a straight line is rise over run. Let's just write in our rise over our run. So here's our rise and here is our run. All right. Why have I picked this point here? And what's this H business all about? Well, what we're aiming to do is get an expression for the gradient of this tangent to the curve here, because that's what we defined on our previous screen as the derivative or the gradient of the curve at that point. The only problem is we've only got one point involved there. That's why I picked another point a little bit up. Now it looks like it's a lot up. That's so that I can show you some working and so forth and put in some values. We've picked a point just a little bit to the right and we've created what's called a chord along the function. This enables us to get the gradient of that chord. Now, assuming that your H value is quite small, therefore that these 2 points are quite close together, it's fair enough to assume that the gradient of the chord will be close-ish to the gradient of the tangent. It's not going to be perfect. And of course, the further away you are, the more likely it is that your estimate by using the chord is not going to be particularly good. But let's work with this one and we'll see how we go. All right, so rise over run. So the gradient of the chord, is our rise over our run. All right, our rise is our change in Y values. This is our new Y value. This is our old Y value. So we have f of x plus h minus f of x. Now what's our run? Our run is our change in our x value. X plus h minus x is h. All right, so that's the first thing we need to know, that the gradient of that chord is f of x plus h minus f of x on h. Remember that because that's going to be a very important part of your formula. Now let's go back to this notion of the fact that we picked a point a little bit to the right. And let's imagine, say I picked this point instead that's a little bit closer. What's going to happen there? What's going to happen if I had a chord between here and here instead? What do you think is going to happen there? Is that gradient going to be closer to this gradient? Well, yes, it will. And in fact, the closer you get, the closer these orange dots get to this point here, x f of x, the closer you will get to the gradient of the tangent. What does that make you think of? Hopefully that's making you think of limits. So what we're saying is, as h is tending towards 0, so as h is getting smaller and smaller and smaller, the gradient of the chord will tend towards what we want, gradient of the tangent. All right. Now we know that the gradient of the tangent is what we said was our f dash x. So let's go with that. So what we're really saying is f dash x is the limit as h tends towards 0 of this expression here, f of x plus h minus f of x all over h. Now we're assuming that h is not 0. We can't divide by 0, and it's okay because we're taking a limit. And hopefully by the time you're watching this video, you will have learnt a little bit about limits. In my next video, I'm actually going to show you how you use this to do some basic examples.